Okay, so we've got these two questions that we want to go through. Now remember what I've said, the reason we're doing these is because we've tried to select, we found this unit reasonably easy, and so I've selected some of the harder questions that they can ask around it. So this one here, question 9, okay? We're going to let's read through it and then I'll talk a little bit about it first. So we've got figure 10 shows a shaded region that is bounded by the functions a of x and b of x. These functions intersect at points 0, 0 and 6, 6. The shaded region is contained within the square formed by the x-axis, the y-axis, x is 6 and y is 6. All right, looks pretty good. Okay, now this next part here, a Monte Carlo experiment. Never heard of it before. A Monte Carlo experiment can be used to estimate the proportion of the square that is shaded and hence estimate the area of the shaded region. The experiment uses the following steps. 1. Independently randomly generate a sample of n points within the square containing the shaded region. Each point within the square has an equal probability of being generated. Number 2. Count the number of these points that are within the shaded region. Number 3. Calculate the proportion of the sample points that are within the shaded region. And this proportion can be used to find the shaded region, to find an estimate of A. The area of the shaded region is p hat times the area of the square. Okay, so hopefully that makes sense, all right? So I want to point this out because this here, all right, it's not something that's part of the subject outline. Monte Carlo experiment doesn't say it anywhere in there. So this kind of simple, I'm reluctant to say it, we're required to comprehend this mathematics, okay? It's not something I'm required to teach, it's not part of the subject outline, it's not something you find in the textbook, but it's something new. You're introducing a new form of mathematics to you, and you need to comprehend it, and now you're going to apply the techniques that we're familiar with in this new circumstance. Okay? So that is one of the things that we'll ask in the exam. Not necessarily Monte Carlo, but things that you might not have come across, but they're going to be techniques that we have done before. So we have a Monte Carlo experiment is conducted using 3 independently randomly generated points. The results are shown in figure 11. We can see the 3 dots there. Part 1. Calculate the proportion of the sample points within the shaded region. Okay, well we have 1 point that's in the shaded region out of 3 points in total. So our value of p hat, based off these 3 independently randomly generated points, is 1 on 3. Alright, so based off that, what does it mean? It would mean the area of the shaded region is about 1/3 of the area of the square. Okay, calculate p hat, done. Part 2. Hence, show that the results for the Monte Carlo experiment indicate that the A is estimated to be 12 square units. Well, we have, if we just look back here, we have the shaded region is p hat times the area of the square. So this is part 2. The shaded region is p hat times the area of the square. Okay, so that's going to be 1 on 3 times, what's the area of the square? Well, it's got a base of 6 and a height of 6. So 1 on 3 times 36 is 12 units squared. Alright, p hat times area of square.
Oh, area.
Yeah. Okay, so, and looking at that, you'd probably say roughly 1/3 anyway, wouldn't you? If you were to look at that and say, yeah, the shaded region is roughly 1/3 around there. Alright, part 3. State why it may be inappropriate to construct a confidence interval for the proportion of the square that is shaded when using a Monte Carlo experiment involving 3 independently randomly generated points. Alright, simple solution. 3 is not very many. 3 is not a large sample size. We should get a better sample size to provide a result that's going to be more indicative of the true proportion. So what do we say for that? 3 is too small of a sample size. 3 is too size. Alright, we should increase n. That's going to give us a more accurate result, and then we'd be more justified in using a confidence interval. Alright, flip the page. A new Monte Carlo experiment is conducted using 1,500, now we're talking, 1,500 independently randomly generated points within the square in figure 10. Of these 1,500 points, 600 are within the shaded region. So we've got 1,500 dots, 600 of them are in the shaded region. Using this information, fill in the boxes below to form a 99% confidence interval, the proportion of the square that is shaded, 99, all right? So if you consider the 99% confidence interval, it's p hat take the lower boundary, p hat take away this value of z alpha and 2, all right? The value of z alpha and 2 for a 99% confidence interval, and that's times p hat times 1 take p hat on top of n. That's going to be the lower point, then we have p, and we have the upper point, don't we? Plus. All right, so the question, we need to start filling in these boxes. Well, our value of p hat is given to us. That's 0.4. That's that 600 divided by 1500. Okay, if you do that, you get 0.4, so we don't need to fill in that part of it. But we do need to fill in this part. All right. So the value of z alpha and 2 for a 99% confidence interval, I've written it down on your in your notes book. So this is one that pops up a bit, 99. So like you can remember it, you can write it down. It's 2.58. But you also are required to know how to calculate them. Okay, so we have done that when we looked at quantiles, z-scores. So, all right, continuing on. So 2.58 is going in the first box, and then in the second box, we're going to have the square root of 0.4 times, well, 1 take away 0.4 would be 0.6. On top of n, the sample size was 1500. So that's going to be the lower sections, the two boxes down there. And then in the upper section, we'll have, again, 2.58, and this time the square root of 0.4 times 0.6 on 1500. Okay, so that's what we're filling in. All right, we'll move on. So that's the first part there, fill it in. And then in the second part, hence or otherwise, calculate the confidence interval. So they want us to evaluate it. All right, so if you want, you can put it in your calculator, 0.5, take away 2.58 times that. That'll take a fair while. I'm not sure what's going to be faster, but I'm just going to go straight to statistics and do it in my stat mode. In stat, we're doing a interval z first proportion, z1 crop. Okay, confidence level 99. I'll write up this information for you. You had 600 out of 1500. So that's the information that we're putting in, and that's going to generate the confidence interval for us. So the confidence interval we get, 0.367, less than p, less than 0.433. Okay, so what does this confidence interval mean? It means based off of this sample of 1500, the shaded region is between 0.367 of the area and 0.433, anywhere in there. But the lowest it could possibly be is 0.367, and the highest it could possibly be is 0.433 area of the square. All right, part 3. A student uses an alternative technique to estimate A and claims that A is at least 14 square units. Provide mathematical evidence that the confidence interval does not support the student's claim. Okay, so if we consider these, all right, the lowest the proportion could be is this, all right, and the highest it could be is this one. So let's take the worst case scenario and multiply that by the area, all right? Remember, if we do p hat times the area of the square, that's going to tell us the area of the shaded region. Now p hat, well, the value of p is somewhere in here, isn't it? It could be as low as 0.367. So let's take that one, 0.367, and if we multiply that by the area of the square, 36, what are we going to get? We've got 13.2. All right, so that means based off of our confidence interval, the true area of the shaded region could be as low as 13.2 units squared. What did the student say? The student said 14. It has to be at least 14. Well, we're 99% confident that it could be this low. All right, so their claim is false. Okay. Next one. Let M be the number of points within the shaded region when 1500 points are randomly generated within the square. Find the smallest value of m that produces a 99% confidence interval that would support the student's claim that A is at least 14 square units. So think about what we did here, like this whole question's been scaffolded. Here we took the lower boundary and multiplied it by the area. So let's go back over to our confidence interval here. This is the lower boundary, isn't it? All right, so I'm going to take that and write that up here. We have p hat, take away 2.58 square root of p hat, 1 take p hat on top of n. That's the lower boundary of the confidence interval. And we need it to be such that when we multiply that by 36, because the area of the square is 36, right? This is going to be our lower proportion. This is the area, such that it equals 14. Because if the lower boundary equals 14, then we have justified the student's claim. All right? Now, we've still got 1,500 points, but they're saying m of them are within the shaded region. And so we're saying, what's the value of m that's going to make this statement true? All right, what's the value of m that's going to make this statement true? So let's sub that in here. What have we got? We've got m on 1,500, take 2.58, square root m on 1,500, times 1 take m on 1,500, on top of 1,500. I'm going to move the 36 over for simplicity. 14 on 36. Okay, so, and then all it is graphing that, or putting it in an equation solver, and solving for n. Alright, so we did this the other day. Alright, I graphed this function, and I'm doing a g-solve, I'm doing an x-calc, when y is 14 on 36, and the value of m you get is 633. Alright, so I'm going to recap this part, because this is the hardest part of this question. What does it mean? It means if you use 633 dots, if 633 of the dots were within the shaded region, then this times 36 would be equal to 14. The student's claim would be justified. Okay, so let's unpack that very last part. They've built you up to it, right? Because what did we do above? We did the lower boundary multiplied by 36. And now we're saying we're going to change the lower boundary. We're going to have a certain amount of points within the shaded region. Here's the formula for the boundary. And you see how they scaffold it, right? They've even done it right at the top. They've given you all those numbers you need. You need all of that information. Okay, so we're taking that. This is the lower boundary. And our new value of p hat is m on 1,500. We sub that in. And then we're just solving that. Okay, so again, the tricky part of this is going to be the comprehension of the question. Coming up with it. Now, what I would like to say about some of these questions, right, is, going around talking to some of you, like, I understand it now that you've gone through it, but I wouldn't know what to do during the question. I'll say two things. Firstly, I mean, that's fine, because in the exam, you've got to be able to sit there and have time to think about it. You haven't thought about this at all. You've just had me get up and tell you exactly how to do it, all right? You're not expected to do that in the exam. In the exam, you're going to have time to read and think about things. And so secondly, the second thing is that's what we want to practice. We want to practice and facilitate that exam situation. I'm in there, I don't know what to do. Let's read it. What are the things that I can do? What things can I write down to get myself some marks? All right, so that's that question. There's two more parts to it. All right, we're not going to do them. We'll just read through them quickly, because what do they do in these last two parts? They give you some functions and they say write an integral expression and find the exact area using integration. So an example of how they've got statistics and integration combined together. All right, so you could go ahead and do that one if you want to, but we'll leave that one for now. All right, the next one's a fair bit shorter. So we'll fly through it. It's a conjecture problem. Okay. We have the function kx to the n times 1 take x. This is the other thing I'll say is, don't assume what the question is asking you. So read it carefully. It's better to be slow and read it deliberately than rush through it and make assumptions and then making stuff up in the maths that you perform. All right? So for positive integer values of n, the function, this one here, forms a probability density function on the interval 0 to 1, given some integer value of k. For this value of k, the function is positive. All right? So it's satisfying the two conditions for a valid probability density function. And then they're going to say, okay, now when n is 1, find k such that it's valid. Alright, so if we've got this statement, this is the function, right? And in part A, they've said n is 1. So that means our function is going to be kx times 1 take x. And it says find k given that it's a valid probability density function. Well, for it to be valid, what are the two properties? It has to be positive. We've already told above that it's always positive. And the second one is that the area over the interval which is valid is equal to 1. So that means we have this. Alright, so straight away I'm going to pull k out front and expand that. Should have my dx's. And then this thing here is going to evaluate to a number. So let's go through and solve it. We're going to have x squared on 2 take x to the 3 on 3 from 0 to 1. Sub in 1. Alright, we have half take a third, that's going to be 1 on 6. And you can do that kind of thing in your calculator, right? You don't have to do those fraction operations manually. So we have k times 1 on 6 equals 1, so therefore k is 6. Alright, so in the circumstance when n is 1, the value of k is 6 is going to make it a valid probability density function. Okay. The other thing is, like it says, algebraically. Okay, so that means you're not allowed to put that in your calculator even after you pull k out. You do need to go through and show that fundamental theory of calculus. Alright, part 2. Find the area under the curve of y equals x squared times 1 take x from 0 to 1. Okay? And this one we will just put straight in our calculator. 1 mark. X squared. Excuse me, I'm in parametric form. X squared, 1 take x, 0 to 1. 1 on 12. Okay, so we're just going to write 1 on 12. Part 2. Hence, find the value of k, that f of x equals k times x squared times 1 take x forms a probability density function between 0 and 1. Alright, so what's the difference between here and here? In our first circumstance, we had this number was 1. In the second circumstance, we've got this number is 2. Alright, so for it to be valid, we're going to have this, right? We have k times x squared times 1 take x from 0 to 1 is equal to 1. That's what it's going to be for it to be valid. Now, what we did in the first part, in the first one, is we factorised k, right? And we know that that part evaluates to 1 on 12. That's what we did in the previous part. So we have k times 1 on 12 is 1. So then k has to be 12 in order for this function, all right, in the circumstance when n is 2, to be a valid probability density function. After considering several more values of n, the following conjecture is made. We've got a conjecture here. In order for f of x equals this to form a probability density function between 0 and 1, k has to equal n plus 1 times n plus 2. Alright? So, all we're doing is taking the general form there, the integral from 0 to 1, k times, we've got x to the n times 1 take x. Okay, that's the function, and it has to equal 1. That's what's going to make it valid. And all we're going to do is solve for k. We're going to show that k equals this. Alright, so we get 4 marks there for doing that. So the first thing we'll do is we're going to factorise k, pull k out the front of the integral, and we're going to distribute this x to the n as well. So what we get x to the n times 1, it's going to be x to the n. And then if I have x to the n times x, they have the same base, so I add the powers. That's where I get n plus 1. That's index laws. Okay, now we're ready to integrate. Everything's expressed in the form of x to the n. So, the integral of x to the n is going to be x to the n plus 1 on n plus 1. Alright, that's just the rule for it. And the integral of x to the n plus 1 is going to be x to the n plus 1 plus 1. Alright, on top of n plus 1 plus 1. Alright, so I'll simplify that in the next step. Do it slowly. Where we have x to the n plus 1 on n plus 1, take x to the 2, x to the n plus 2. In the next step, we'll substitute in the numbers that we have. So this k is hanging out the front. We're going to have 1 to the n plus 1 on n plus 1. Take 1 to the n plus 2 on n plus 2. Alright, I'll stop for a sec. Alright, and we can evaluate it further because 1 to the power of anything equals 1. So here, what this is going to simplify to is 1 on n plus 1, take 1 on n plus 2. Alright, and then over here, 0 to the power of n plus 1, that's 0, divided by that. This doesn't matter, that whole thing is going to 0. So we're left with this equals 1. I'll come back up here, you should have a bit more room. So we have, k times 1 on n, I'm just going to restate it so I can write it up here, n plus 2 equals 1. So what we're trying to do is get k by itself, right? And so what we'll do is we want to join those together and move that over. So what we should do here is multiply both sides, cross multiply the denominators, right? We're going to multiply this one by n plus 2 on n plus 2, and this one by n plus 1 on n plus 1. So what we'll get when we do that, I'll cross multiply. We'll have n plus 2 So if you're not sure about that, put an asterisk there and I'll explain that step, how we're joining those two fractions together. Alright, and then what does that simplify to? At the top here we have n take away n, so that will cancel. And we have 2 take away 1. So we're going to be left with 1 on top of n plus 2 times n plus 1 equals 1. And now we multiply both sides by this denominator, QED. Alright, so if k is that value, then this probability density function will be valid for any value of k or n. Alright, so these are hard questions, right? And I have taken them from the end of the exam, so they tend to be the harder ones towards the end. But we're just going to practice them and get better at them. But yeah, there's a couple of questions there to go. So let me know if you have any questions about it all. But other than that, let's direct our efforts towards test revision for the test tomorrow.